welcome to this problem walkthrough. Today, we'll be tackling problem number 1307, titled Verbal Arithmetic Puzzle, which is an exciting challenge that tests your logical reasoning and problem-solving abilities. Let's dive in and explore the problem together. In this problem, we are working with an equation where words are used to represent numbers. Each letter in these words corresponds to a unique digit between 0 and 9. The goal is to assign digits to letters such that the equation holds true, treating the words as numbers. For example, in the equation send plus more equals money, each word represents a number, and your task is to determine if there's a way to assign digits to letters so that the sum of send and more equals money. Keep in mind, no word can start with the digit 0 unless the word itself is 0. The input consists of a list of operand words and one result word, and the output will be true if such an assignment exists, and false otherwise. To clarify the output further, the solution should return true only if there is a valid mapping of letters to digits that satisfies the equation. Otherwise, it returns false. Let's look at an example. If the input words are send, more, and the result is money, the output should be true. In this case, a valid digit assignment could be s equals 9, e equals 5, n equals 6, d equals 7, kim equals 1, o equals 0, r equals 8, and y equals 2. This assignment ensures that the sum of the numbers represented by send and more equals the number represented by money. Using the assignment from the previous example, we can calculate the numeric values of the words. Send would translate to 9567, more to 1085, and their sum is 10,652, which matches the value of money. Since the equation is satisfied with this assignment, the output is true. Now consider another example. If the input words are 6, 7, 7, and the result is 20, it's possible to find a valid assignment of digits to letters that satisfies the equation. In this example, a valid assignment might be s equals 6, I equals 5, x equals 0, e equals 7, v equals 1, n equals 2, t equals 8, w equals 9, and y equals 3. With this mapping, 6 becomes 650, 7 becomes 6871, and adding these together gives 20, which equals 14392. Since the equation holds true with this assignment, the output is true. However, there are situations where it's impossible to find a valid digit assignment. Let's look at one such example. Imagine the input consists of the words, LeetCode, and the result is point. In this case, no matter how digits are assigned to letters, it's not possible to satisfy the equation. As a result, the output will be false. This demonstrates that not all input cases will have a solution, and the algorithm must correctly identify when the equation is unsolvable and return false. There are a few constraints and edge cases to be aware of. The number of operand words will range from 1 to 5, and both the operand words and the result word can have a maximum length of 7 characters. All strings consist of uppercase English letters, and there can be at most 10 unique characters across all input words and the result. It's also important to ensure that no word has leading zeros unless it's the word 0. Edge cases include small inputs, such as a single operand word, and large inputs where word lengths are at their maximum. Additionally, the solution must handle unsatisfiable cases correctly, returning false when no valid assignment of digits to letters exists. These considerations will ensure the solution is robust and handles all possible scenarios. To begin with, one straightforward approach we might consider is the brute force method. The intuition here is quite simple. We try mapping all possible digits, from 0 to 9, to the unique letters in the problem. Once we have a mapping, we compute the numerical values of the words based on this mapping and check if the equation balances. To break it down, the process involves extracting all the unique letters from the input words, generating every possible permutation of digits for these letters, and then evaluating the equation using these mappings. While this approach is conceptually easy to understand, the computational cost is significant. With at most 10 unique letters, we end up generating 10 factorial permutations, and for each permutation, we need to evaluate the equation. This results in an O(10) m time complexity, where m is the cost of evaluating a single equation. The trade-off here is clear. While simple to implement, this approach becomes infeasible as the number of unique letters grows due to the rapid factorial growth of permutations. Now, to improve efficiency, we turn to backtracking with pruning. Instead of blindly testing all permutations, this approach incrementally assigns digits to letters and uses constraints to eliminate invalid mappings early. This way, we avoid exploring paths that cannot possibly lead to a solution. There are a few key observations that make this method work. For example, a letter's position in a word determines its numerical weight. Leading zeros are not allowed unless the word is specifically zero, and constraints like digit-wise addition can help validate partial solutions. The process involves a recursive function that assigns digits one by one, checking constraints at each step. If a constraint is violated, the algorithm backtracks to try a different assignment. This method is far more efficient than brute force because it prunes large portions of the search space. With a reduced complexity of OK, where K is the number of unique letters, this approach is both practical and effective for typical problem sizes. However, it's worth noting that the efficiency of this method still depends on how well the constraints are managed during recursion. For even greater optimization, modern constraint programming tools provide an alternative solution. These tools, such as OR tools, allow us to model the problem as a set of constraints and solve it using advanced techniques like arc consistency and domain reduction. The advantage of this approach lies in its efficiency. These solvers are specifically designed to handle constraint satisfaction problems and can often find solutions faster than custom algorithms. Additionally, using a library minimizes implementation effort, as much of the heavy lifting is handled internally. However, there are trade-offs. For one, you have less control over the solution process, which may be important if you need to customize the algorithm for specific scenarios. There's also some overhead in setting up and utilizing the library. While this approach is powerful, it may not always be the best fit depending on the problem requirements and the level of control desired. Ultimately, we chose backtracking with pruning as our primary strategy for solving the verbal arithmetic puzzle. This method strikes the right balance between simplicity and efficiency. While brute force is easier to conceptualize, its factorial growth makes it impractical for large inputs. On the other hand, constraint programming is highly optimized but comes with dependencies on external tools and limited control over the process. Backtracking with pruning allows us to directly leverage problem-specific constraints, like avoiding leading zeros and validating digit-wise addition, to prune invalid mappings early. This significantly reduces the computational effort. Moreover, this approach is flexible, enabling us to incorporate additional constraints as needed, and scalable enough to handle typical input sizes effectively. By carefully managing constraints during recursion, we achieve a strong balance of performance and ease of implementation. In summary, this strategy provides the best trade-off between complexity, efficiency, and practicality for this problem. To solve the verbal arithmetic puzzle, we start with the brute force approach by breaking the problem into manageable steps. First, we identify all the unique letters in the given equation. This involves parsing the input to extract each distinct letter from the words and the result. For example, in the equation sen plus more equals money, the unique letters are S, E, N, D, M, O, R, and Y. This step is crucial because the number of unique letters determines whether the problem is solvable. If there are more than 10 unique letters, it's impossible to map them to the digits 0 through 9. Next, we generate all permutations of digits for these unique letters. Using a permutation generation algorithm, we create every possible way to assign digits to the letters. For instance, if there are 8 unique letters, we need all permutations of 8 digits from the pool of 0 through 9. Since the number of permutations grows factorially, this process can become computationally expensive as the number of unique letters increases. It's a simple but exhaustive way to explore all possible solutions. After generating the permutations, the next step is to map these digits to the corresponding letters. For each permutation, we assign digits to the letters and substitute the values into the words. For example, if a permutation assigns S equals 9, E equals 5, N equals 6, D equals 7, M equals 1, O equals 0, R equals 8, and Y equals 2, we substitute these values into the words send, more, and money. Once the mapping is done, it's important to check for constraints. Words cannot start with the digit 0, so assignments like S equals 0 and send or M equals 0 and more are invalid. This ensures the mappings respect the rules of numerical representation. Then, using the current mapping, we compute the numerical values of each word. For instance, send becomes 9567, more becomes 1085, and money becomes 10652. Finally, we validate the equation by comparing the left-hand side, which is the sum of send and more, to the right-hand side, money. If the two sides match, we have found a solution. Otherwise, we move on to the next permutation and repeat the process. When a valid mapping is found, we output the solution. For example, the solution could look like S equals 9, E equals 5, N equals 6, D equals 7, M equals 1, O equals 0, or equals 8, Y equals 2. This mapping satisfies the equation send plus more equals money. However, if no solution exists after testing all permutations, we terminate the process and report that the equation cannot be satisfied. It's important to note a few key insights about this brute force approach. The complexity arises from the factorial growth of permutations as the number of unique letters increases. While this is feasible for up to 8 unique letters, it becomes computationally intractable for higher numbers. To optimize, we can prune invalid permutations early, for example, by skipping those that violate the leading zero constraint. Additionally, recognizing symmetrical properties in the equation or using domain-specific heuristics, such as prioritizing assignments for leading letters, can drastically reduce the number of permutations we need to test. To implement this approach efficiently, several data structures are essential. First, a set is used to store the unique letters extracted from the equation. This ensures we avoid duplicates and can perform membership checks quickly. Next, a list is used to store the permutations of digits that will be assigned to the letters. Since the brute force method involves testing each permutation sequentially, lists are ideal for this purpose. A dictionary is another critical data structure, as it maps each letter to its assigned digit during a specific permutation. This mapping allows for efficient letter-to-digit lookups when validating the equation. Finally, strings are used to represent the words and the equation itself. Strings make it easy to parse the input equation and substitute letters with their corresponding digits during the computation and validation steps. The solution relies on several key operations. Parsing the equation is the first step, where we extract all the unique letters efficiently. Then, we generate permutations of digits using algorithms like Heap's algorithm or Python's itertools.permutations, which are well suited for this task. Validation involves converting each word into its numerical equivalent using the current mapping and checking whether the equation holds true. To improve efficiency, pruning invalid permutations early is a critical optimization. For instance, if a mapping results in a leading zero for any word, we can skip further validation for that permutation. Addressing edge cases is also vital. If the number of unique letters exceeds 10, the problem is unsolvable, and we can terminate early. Similarly, we must enforce that no word starts with a leading zero. In scenarios where multiple solutions exist, we may need to return all valid mappings instead of just one. Finally, we need to handle situations where no valid solution exists. After testing all possible permutations, if none satisfy the equation, we conclude that the problem has no solution. This ensures the algorithm can gracefully handle unsolvable cases while providing a clear outcome. By combining these steps, optimizations, and edge case handling, we construct a robust approach to solving the verbal arithmetic puzzle, balancing correctness and computational feasibility. Here, we start by importing the permutations function from the itertools module, which will allow us to generate all possible arrangements of digits later on. Then, we define a class called solution, and its primary method is solvable, which takes two arguments, words and result. The first step inside the method is to gather all unique letters from the input words and the result string. This is done by concatenating all the words and the result, and then converting the combined string into a set to extract unique characters. Since we can only map at most 10 letters to the digits 0 through 9, we perform a quick check to see if the number of unique letters exceeds 10. If it does, we immediately return false, as the problem would be unsolvable. Next, we convert the set of unique letters into a list for consistent indexing, and we identify the first letters of all words, including the result. These first letters are important because they cannot map to the digit 0, as that would create invalid leading zeros in the numbers. We then define an inner function, compute_value, which is responsible for checking whether a given mapping of letters to digits satisfies the arithmetic equation. This mapping is represented as a list of digits passed to the function. Inside compute_value, we create a dictionary that maps each letter to its corresponding digit based on the provided mapping. Using this dictionary, we define another helper function called word_to_number, which converts a word into its numeric equivalent by replacing each letter with its corresponding digit. Finally, compute_value calculates the numeric values of all the input words and the result, and checks if the sum of the word values equals the value of the result. If it does, the mapping is valid, and we return true. Now, we move on to the core logic of solving the puzzle. To evaluate all possible assignments of digits to the letters, we use a for loop to iterate over all permutations of the digits 0 through 9, with the number of digits equal to the number of unique letters. Each permutation represents one potential mapping of letters to digits. Before processing a permutation, we ensure that no letter mapped to a leading position in a word is assigned the digit 0. This is achieved by checking whether any of the first letters corresponds to 0 in the current permutation. If such a case exists, we skip this permutation and continue to the next one. If the current permutation passes the leading 0 check, we call the compute_value function with the permutation as the argument. If compute_value returns true, it means we have found a valid mapping where the sum of the words equals the result, and we return true to indicate that the puzzle is solvable. If none of the permutations result in a valid mapping, we return false at the end, indicating that no solution exists for the given input. This approach systematically explores all possible combinations while ensuring that the constraints, such as no leading zeros, are respected throughout the process. To start, we first import the necessary Java utilities and define the main is_solvable method. This method takes an array of strings, representing the input words, and a single string for the result. The first step is to gather all the unique letters from both the words and the result. These letters are stored in a hash set, ensuring that no duplicates exist. The reason for this is that each unique letter must eventually be mapped to a distinct digit. Next, we check if the number of unique letters exceeds 10 since digits range from 0 to 9. If there are more than 10 letters, it's immediately impossible to solve the puzzle, and the method returns false. After confirming the letters are within the limit, we convert the hash set into a list for easier indexing. Additionally, we identify the first letter of each word, as well as the first letter of the result, because these letters cannot be mapped to the digit 0 in the final solution. This ensures that no word or result starts with an invalid leading 0. Now, we move on to converting the words and the result into their numerical representations based on their positional values. To do this, we iterate over the input words and calculate their word values using the compute_word_value method. This method takes a word and the list of letters and generates a numerical value by replacing each letter with its index in the list. The result string is also converted into its corresponding numerical value using the same logic. With these numerical representations, the next challenge is to test all possible mappings of letters to digits. This is achieved by calling the checkPermutations method, which takes in the list of letters, the set of first letters, the calculated word values, and the result value. This method will systematically explore every permutation of digit assignments and validate if any of them satisfy the constraints of the puzzle. Within the checkPermutations method, we define a helper function called permute, which performs the recursive backtracking to generate all possible mappings. The permute method operates by mapping each letter to a digit, one at a time, while ensuring that the constraints are respected. For example, if the current letter is a first letter of any word or the result, it cannot be assigned the digit 0. The method also avoids reusing any digit that's already assigned to another letter. At each step, the mapping is updated with the current letter to digit assignment, and the recursion progresses to the next letter. If all letters are successfully assigned, the validate mapping method is called to check if the current mapping satisfies the arithmetic constraints. If the mapping is invalid, the method backtracks by removing the last assignment and continues exploring other possibilities. This process continues until either a valid mapping is found or all permutations have been exhausted. Finally, the validate mapping method ensures that the current mapping actually satisfies the equation formed by the words and the result. It calculates the sum of the mapped values for all the input words and compares it to the mapped value of the result. The map value method plays a key role here by converting a numerical value into its mapped equivalent using the current letter-to-digit mapping. For each digit in the numerical value, it appends the corresponding mapped digit to a string, which is then converted back into an integer. If the sum of the mapped word values matches the mapped result value, the mapping is valid, and the solution is considered correct. Otherwise, the recursion continues exploring other permutations. This comprehensive approach ensures that all constraints of the verbal arithmetic puzzle are respected, and the solution is both accurate and efficient. To solve the verbal arithmetic puzzle, we begin by parsing the input. In this example, the words are sen and more, and the result is money. From these, we extract the unique letters S, E, N, D, M, O, R, and Y, giving us a total of 8 letters. Additionally, we identify that the first letters of the words S and M cannot be mapped to 0, as they appear in the most significant positions. Next, we generate all possible permutations of digits from 0 to 9 for these 8 unique letters. While doing so, we enforce the constraint that S and M are never assigned the digit 0. Once we have these permutations, we can test them to see if they satisfy the equation. For instance, consider the mapping S equals 9, E equals 5, N equals 6, D equals 7, M equals 1, O equals 0, R equals 8, and Y equals 2. This mapping will be used for the next steps. Now that we have a potential mapping, we can convert the words into their numerical equivalents using this mapping. First, sen becomes 9567 by calculating 9 times 1000, plus 5 times 100, plus 6 times 10, plus 7. Similarly, more becomes 1082, derived from 1 times 1000, plus 0 times 100, plus 8 times 10, plus 2. Finally, money becomes 10,852, calculated as 1 times 10,000, plus 0 times 1000, plus 8 times 100, plus 5 times 10, plus 2. To validate this mapping, we check whether the equation 9567 plus 1082 equals 10,852 holds true. In this case, it does, so this mapping successfully solves the puzzle. In the next example, we simplify the problem to the words at NB, with the result being C. Parsing the input reveals just 3 unique letters, A, B, and C, all of which must be mapped to digits. Since each of these letters is a first letter, none can be assigned the digit 0. We then generate all possible permutations of 3 digits from 0 to 9 to map these letters. For one of these permutations, let's try mapping A to 1, B to 2, and C to 3. This mapping will be tested to see if it satisfies the equation. Using the mapping A equals 1, B equals 2, and C equals 3, we proceed to convert the words into numbers. The word A directly translates to the number 1, B becomes 2, and C becomes 3. With these numerical values, we validate the equation by checking whether 1 plus 2 equals 3. The result is true, confirming that this mapping successfully solves the puzzle. In this third example, we solve the puzzle for the words leet and code, which result in point. Parsing the input identifies 9 unique letters, L, E, T, C, O, D, P, I, and N. Of these, the first letters L, C, and P cannot be assigned the digit 0. To solve, we generate all possible permutations of digits from 0 to 9 for these 9 letters. One potential mapping is L equals 9, E equals 8, T equals 7, C equals 6, O equals 5, D equals 4, P equals 1, I equals 0, and N equals 2. This mapping will be tested to see if it satisfies the equation. Using the mapping L equals 9, E equals 8, T equals 7, C equals 6, O equals 5, D equals 4, P equals 1, I equals 0, and N equals 2, we convert the words into numbers. Leet becomes 9,887, calculated as 9 times 1000, plus 8 times 100, plus 8 times 10, plus 7. Code becomes 6544, derived from 6 times 1000, plus 5 times 100, plus 4 times 10, plus 4. Finally, point is 10,287, calculated as 1 times 10,000, plus 0 times 1000, plus 2 times 100, plus 8 times 10, plus 7. To validate, we check whether 9,887 plus 6,544 equals 10,287. This equation does not hold, so this mapping does not solve the puzzle. We would then move on to the next permutation and repeat the process until a valid solution is found or all permutations are exhausted. For the examples we've looked at, the output is true for the first two cases, while for this third example, no valid mapping was found, resulting in false. The time complexity analysis begins with understanding the brute force nature of the solution. Since we are checking all possible mappings of letters to digits, the first thing to note is the number of unique letters, denoted as L. This value is at most 10, as there are only 10 digits available from 0 to 9. If the number of unique letters exceeds 10, the function immediately returns false because it's impossible to create a valid mapping. For valid cases where L is 10 or fewer, we compute the total permutations of these letters using the formula P, 10, L, which is 10 factorial divided by 10 minus L, factorial. This represents all possible arrangements of L letters with the 10 digits. In the worst-case scenario, where L equals 10, this results in 10 factorial, which is approximately 3.6 million permutations. This exponential growth highlights the computational intensity of this approach as L increases. For each permutation, the algorithm performs several validation steps to determine whether the current mapping satisfies the given equation. First, letters are mapped to digits, which takes L time as we construct a dictionary for this purpose. Next, each word in the input is converted to a numerical value using this mapping. For a word of length W, this conversion requires W time. If there are n words in total, including the result, the overall cost of converting all words is W underscore total, where W underscore total is the sum of the lengths of all words. Finally, the validation involves summing up the numerical values of the words and comparing the result, which takes n time. Combining these steps, the time complexity for validating a single permutation is L plus W underscore total plus n. When considering all permutations, the total time complexity becomes P, 10, L, asterisk, L plus W underscore total plus n. In the worst case, where L equals 10, this evaluates to approximately 3.6 million asterisk, 10 plus W underscore total plus n, illustrating the factorial growth of the problem as the number of unique letters increases. The space complexity is determined by the storage requirements at various stages. First, the letters list, which stores all unique letters, requires L space. Similarly, the letter underscore to underscore digit dictionary, which maps these letters to their corresponding digits during validation, also requires L space. The permutations function generates mappings one at a time, so it does not store all permutations in memory simultaneously. However, the space required for the current permutation being processed is L. Temporary storage is also needed for converting words into numerical values. For a word of length W, this conversion requires W space, and since this process occurs sequentially for all words, the maximum storage at any point is determined by the longest word, denoted as W underscore max. Importantly, the function does not use recursion, so there is no additional call stack overhead. Combining these factors, the total space complexity is L plus W underscore max, where L is the number of unique letters, and W underscore max is the length of the longest word. The brute force approach checks all possible mappings of letters to digits, making it computationally expensive for larger values of L. While this guarantees correctness, it does not optimize the search process. For smaller values of L, the approach is feasible, but as L approaches 10, the number of permutations becomes prohibitively large. To improve efficiency, optimized techniques can be introduced. For example, logical constraints such as digit ranges or rules that eliminate mappings with leading zeros can help prune the search space. Additionally, techniques like constraint satisfaction or backtracking with pruning could systematically explore only the most promising mappings, significantly reducing the number of permutations that need to be validated. Analyzing the best, average, and worst cases provides further insight into the solution's behavior. In the best case, a valid mapping is found early in the permutation process, and the function terminates without exploring all possibilities. This results in a time complexity of P, 10, L, asterisk, L plus W underscore total plus n, where L represents the subset of permutations checked before finding the solution. On average, roughly half of all permutations are checked, leading to a time complexity of approximately P, 10, L, /2 asterisk, L plus W underscore total plus n. In the worst case, all permutations are explored, yielding the full factorial growth of O, P, 10, L, asterisk, L plus W underscore total plus N. This factorial growth makes the solution computationally expensive as L increases. To address this, advanced optimizations like constraint propagation or backtracking could significantly reduce the number of permutations, making the approach more practical for larger inputs. When solving verbal arithmetic puzzles, there are some common mistakes to watch out for. First, be cautious about leading zeros. Many problems explicitly prohibit numbers with leading zeros, so you'll need to ensure that your mappings don't result in invalid numbers. For example, if you map the letter A to 0 in an equation like AB plus BC equals CA, it could create a number starting with 0, which is not allowed. Next, remember that each letter must map to a unique digit between 0 and 9. Forgetting this constraint, like assigning the same digit to two different letters such as at NB, will break the rules and lead to invalid solutions. Another critical point is understanding the limitations of brute force approaches. Since brute force involves permuting digits, the complexity grows factorially, and if the number of unique letters exceeds 10, the search space becomes infeasible. Lastly, be aware of non-alphanumeric characters in your input, such as plus or equal sign, as overlooking them can lead to parsing errors or incorrect mappings. Always ensure your solution accounts for these characters correctly. Now, once you've generated a potential solution, it's essential to validate the final equation. For example, if you solve for sin plus more equals money, you need to substitute the digits back into the equation and confirm that it holds true. Skipping this step can lead to incorrect or incomplete solutions. In interviews, your ability to recognize patterns and constraints is often tested. For instance, identifying leading zero restrictions or ensuring unique mappings early on can demonstrate strong problem-solving skills. It's also important to discuss the time complexity of your approach. A naive brute force solution has a factorial complexity of O(10), which can be prohibitively expensive. Proposing optimizations, like pruning invalid mappings early, shows that you're thinking critically about efficiency. Lastly, don't overlook edge cases. Be prepared to handle scenarios like inputs with no solution, fewer than 10 unique letters, or invalid formats. Discussing these proactively can make a strong impression on your interviewer. To deepen your understanding of verbal arithmetic puzzles, there are several related problems worth exploring. For example, in LeetCode 306, additive number, you work with sequences where each number is the sum of the previous two, which builds on similar logic. LeetCode 52, nqueens2, demonstrates backtracking concepts that are directly applicable to solving these types of puzzles. LeetCode 1079, letter tile possibilities, involves permutations, which is also closely related. And LeetCode 282, expression add operators, focuses on generating valid expressions, which can help you practice equation validation. When tackling these problems, consider alternative approaches. Backtracking with constraint pruning is a common technique, as it narrows the search space by eliminating invalid mappings early. However, it can still be computationally expensive for larger inputs. Heuristic search is another option, where you make educated guesses to prioritize likely mappings. This can be faster, though it might miss some solutions. Occasionally, dynamic programming can be adapted to these problems, but it's rarely applicable due to the nature of the constraints and permutations involved. To summarize, success with verbal arithmetic puzzles comes down to understanding constraints and edge cases. Always take time to articulate these during interviews, as it demonstrates critical thinking and thorough problem solving. Start by discussing the brute force approach, it's the most intuitive, and then propose optimizations to show how you can make the solution more efficient. Finally, leverage related problems to practice the core techniques that these puzzles rely on, such as backtracking, permutation generation, and constraint validation. These skills will not only improve your performance on this problem type but also strengthen your overall problem-solving toolkit. Great job making it to the end. In summary, we tackled a verbal arithmetic puzzle and explored the brute force approach. Remember, while brute force lays the groundwork, optimization is key for efficiency. Thanks for watching, and stay tuned for more problem-solving adventures. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!